Hello, ladies and gentlemen from Earth. Welcome back, and today we're continuing our studies on regression. So in the previous episode, we saw about simple regression. I ran through some example, and today I'll explain the core concepts of multiple regression and run through some example I created as well. Alright, gonna be pretty fast and pretty easy. Since we already know what simple regression is, multiple regression is basically the same thing, but we use more than one independent variable, okay, in multiple regression. Instead of having just one x here, one input, we'll have two or more inputs, alright? So it means that you're not fitting a straight line anymore, a diagonal line. We're fitting a hyperplane, which is a flat surface in a high-dimensional space, okay? It's gonna be easy to see when I show you the graph, but it's not a line anymore. It's still linear regression though. Why? Because the coefficients here are the theta 1, theta 0, theta 2. They're being summed up in the end. So the math here is really simple, even if the results can be a little more complex than the simple regression. Some things to consider is that too many variables can cause overfitting to our model. So we're not gonna use all the variables always, okay? We gotta clean them and study them. Like some categorical independent variables, they can be useful to us. But for them to be useful, we gotta either convert them as numbers or create a new column to convert them as numbers if they are more than like 2. The applications are basically the same as simple regression. We use to predict the relationship between a target variable and features, except that in multiple regression it's in plural, so it's more than one feature. So for the example I used it in the last video, I used it to predict the Pokemon's total, which was kind of a mess because attack cannot predict a Pokemon's total. But here with multiple regression, we'll use all the other features to predict the total, okay? So there's one application. We can predict an AI behavior in a game. For example, imagine that you have a board game here in computer, and there's AI, and you can predict the success of a certain action, given some features, and the value you wanna to predict, either percentage of an action, or maybe the damage dealt. So let's say we want our AI to predict the highest damage dealt action possible. We can use multiple linear regression. And there's also what if scenarios. We can predict what if scenarios in simple regression as well, but multiple regression, it makes them easier to be predicted because we have multiple features. So you can like, what if adjust drop rates? What will happen with the player progression if we adjusted the drop rates for a certain monster or a certain dungeon? We'll have some features, and then we can predict the player's progression. And we gotta be careful with some features that can be highly correlated to other features, because if they are too correlated, they will be predictors of each other. That's why it's important to reduce variables that is not going to be useful and just select variables that will be useful to us, okay? There's a hyperplane I talked about earlier, but it only allows us to show up to 2 variables, okay? Two features. So given a y-hat target here, we'll have 2 features, and we can plot it in a hyperplane like this. Regression models that have more than 2 features will be trickier to plot in the graph. It will be a 3-dimensional graph, but we'll get to this later. So for evaluation, it's basically the same as simple linear regression. We will use MSE, okay, not the only one, but the most popular one, and it's basically doing the same computation as the simple linear regression, right? So you will take the difference between the true value and the predicted value by the model. We'll have the mean of these differences, and then we get an idea of how poorly our model is predicting, okay? By the way, if you have a larger data set, we'll probably be using gradient descent. It's a technique to find the coefficients by putting some random values to it until the model converges, which is where converging a model is the point that it has the best coefficient. So let's get to the code. I'll skip the import, we already know that, and also load data, getting the sample, the basics. Just a disclaimer here, the describe function omits category values by default. These measures like mean and standard deviation, they are not defined for string data, right, or category values, but you can include them passing include is equal to object. Usually it's not good to modify our data frame directly. In this case, it's pretty clear the columns we want to drop here, because we're not using any category values. They're not available to us here in this example, right? Because we want to predict the total, and we just need the Pokemon stats, not the generation, or whether it's a legendary or not, or type or anything. So we can just drop it, and we can check it. We can check our data frame to see if it's dropped, and then we're gonna use this core function that displays the correlation between all the features, right? The correlation goes from -1 to 1, and the sign is just the direction, so it's either going upwards or downwards, if you can say that, or left or right, just the direction. So like 1 here is a full correlation, and -1 is a full correlation as well, just other direction. And here you want to eliminate any strong dependencies or correlations between the features. In our case, we don't have any, so we're gonna use all of them. And of course, we're gonna drop the hash. It's the Pokédex index, and there's no correlation with our stats nor our total. Now let's print the first 6 Pokémons in the Pokédex and see our data frame. Now it has only total and our features that we're gonna use it. And another way to help us selecting the features that will be useful is by plotting a scatter matrix, right? It shows the scatter plots for each pair of input features, and the diagonal here is our histogram. So we don't need to use the histogram function as we did in the previous code. We just plot a scatter matrix and we have everything here. And basically here we wanna run a flatten, so basically turning them into a one-dimensional list, and we're gonna rotate the axis so we can get a better reading for our labels. And how do we read this? So the shape of our data is pretty obvious. They are our histograms in the diagonal part here. And then we wanna look at our output variable, or our total, in the y-axis, right? And compare with our features in the x-axis. So we can see here our total and HP, attack and defense, and so on. We want to take a look at this part of the graph to see the correlations between our features and our output variable, or our target variable. Here you just want to see a linear correlation basically. So everything that seems linear will be a good fit for us. All of our features are basically the same here, excluding HP. Now we can extract our input and output variables. Remember, output will be always 1 here. We want to extract our rows, so our data frame, and 1 column, because the column is what we want to extract here. And here to check whether it's right or wrong, we can always run a sample of our data, or head, or whatever, and we just gotta check the index here. So our index for our target variable is 0. Remember that arrays always start with 0, so our target variable is 0. And then 1, 2, 3, 4, 5, 6. So we pass 7 because it's up to but not including the 7th place. Now here's the part of pre-processing, and what I want to do is we want to standardize our data. We can do that by running the standard scalar method, and basically I have the other variable for x here that will be our standardized features, and we can display here the standardized against the non-standardized data statistics. These 2 graphs will be useful to explain some things here. So standardizing data is important to our model not to think that some feature X is more important than other because of its size, okay? And what I mean by size is by number here. For example, our column 0, which is our HP, it has a minimum of 1 and maximum of 255. In the other hand, 5 has a minimum of 5, but a maximum of 180. So the model might think that HP is more important because of its magnitude. So you wanna standardize it. We can also see that with our mean and standard deviation, which are different from each other, and it shouldn't be different, alright? So the model can measure all the features as the same weight, and we just pass the weight if it's needed after. So here in our standardized data, we have a mean of 0 and a standard deviation of 1, which is what we want. We do the same process as before, split the data, train the model, and boom, we get our coefficients and intercept. Here we have a bunch of coefficients because it's multiple linear regression, so many features, one coefficient per feature. Now the visualization is a bit tricky because we have a 7-dimensional problem. It is a 6-dimensional problem actually, but let's put here 7 because it counts with the target variable. So we cannot use 2D or 3D plots. So we cannot use plane plots as I showed it before in the notes in my notebooks. So the best way to visualize our model is to plotting the predicted versus the actual values. Here the sample I took will be kind of bad because our model will be perfect. And why is that? Why our model is perfect? And shouldn't it be always that? No, it shouldn't. Okay. Usually when you do a model, it's not gonna fit every point on the graph because it's overfitting. The total stats of a Pokemon is exactly the sum of all the other stats. So that's why it's perfect. Everything our model needs to do, it's basically have the same weight for each feature, and then we always predict our exact target variable. So yes, I chose a bad example, didn't calculate it, so my bad. And I just show you if I plotted a 2 or 3-dimensional graph here. It's pretty poor because it's basically ignoring all the other stats for the target variable, and actually it doesn't, and actually shouldn't ignore, and our model isn't ignoring, so it just doesn't work. It gets really weird, and showing a 3D plane we could show with a hyperplane, but again it's up to 2 features and it's gonna look weird as well because I have more than 2 features. So for evaluation, as I said, it's basically the same thing. You can run the same code and evaluate the same metrics. We just run that. We can see that our MSC and MI is 0 because our model is perfect, as well as our R2 score is 1 because it is perfect. Okay. Not a very good example, but I guess I could show you guys how to evaluate the features well, how to choose them, and how to train a model for multiple linear regression, which is basically pretty much the same as simple regression, but with more features. That's it for today. Next up, I'll be explaining about polynomial and nonlinear regression. That will be a harder lesson, probably. I'm still struggling to understand them, but yeah, thank you guys. See you all later.